Okay, one last thing before we finish up with DC circuits. We didn't talk about power, which your book talks about in the chapter on resistance. So I just want to derive an equation really, really quickly, and it's just a couple of simple linear equations to use, so we'll leave it at that. If we look at Ohm's law, voltage equals current times resistance. And we think about what's happening in an electrical circuit. We've got some source of electrical potential difference, like a battery, and that is pushing electrical charges through a circuit which has some resistance, either because it has a physical resistor in the circuit, or because there's a light bulb, or there's a motor, or there's a heating element, or whatever circuit you're pushing electrons through, there's some kind of resistance. And we talked about what happens in a resistor is those electrons are banging their way through that metal, and on the microscopic level, they are delivering some kinetic energy to the atoms that make up that metal, and some of the energy of those electrons is actually going into heat. In something like a stove or an iron or a light bulb, an incandescent light bulb, that's intentional. What we're doing with that device is we're trying to make heat with electricity. In a regular electrical circuit, sometimes that's incidental. We're not trying to make heat, but we make heat anyway. If you've ever picked up your laptop charger, you'll notice that it is hot. The current running through that laptop charger is generating a large amount of heat all the time. So we can talk about the amount of energy dissipated by an electrical circuit in terms of its resistance, the amount of energy stored in the battery as chemical potential energy or electrical potential energy that's being dissipated in a resistor, or as in the circuit as a whole, being dissipated as heat. So if we ask ourselves, what is this V in this expression? Remember, voltage is potential energy per unit charge. And so if we write that just delta E, how much does the energy of the battery change per unit time? Per charge flowing through the circuit. That's equal to IR, so we got the change in potential energy of the battery is QIR every time a charge leaves the battery. And if we divide both sides of this equation by time, we've got delta E over delta T equals delta Q over delta T times I times R. Delta Q delta T is just current again. So that's I times R equals I squared R. Change in energy over time is power, right? Power is the amount of energy change of a system over unit time. Power is measured in joules per second. A joule per second is a watt. And the power used by an electrical circuit, or the power dissipated by an electrical circuit, is equal to I squared R. The electrical potential energy stored in that battery is being converted into either heat or work if it's running a motor, and that work is given by the square of the current times the resistance. So there's actually two closely related formulas for power in an electrical circuit. Power is equal to I squared R. If we use V equals IR, we can write this. What we do is we take one of these I's and write it as V over R. So I squared R equals V over R times I times R. The R's cancel, and this is also equal to IV, the current times the voltage. So either of these things either of these formulas, I squared R or I times V, current times voltage, we can use to calculate the power dissipated by an electrical circuit. If we know the current and the resistance, or we know the current and the voltage. These are just simple, straightforward formulas that you plug numbers into. There's nothing complicated about calculating the power in an electrical circuit. Is there anything else to even say about that? We could check to make sure that both of these things give us units for power, give us units of a joule per second. I think if we do that, we'll find that, for example, for IV, it's pretty straightforward that current is measured in amps, which is a coulomb per second. Volts is energy per unit charge, so, well, I'm running out of space here. Let's write this again. Power equals IV. Potential energy is voltage is potential energy per unit charge, right? So that's a joule per coulomb. So power is equal to a coulomb per second, an amp, times a volt, which is a joule per coulomb. The coulombs cancel. That gives us a joule per second, and a joule per second is equal to, by definition, a watt. So you can see that this equation gives watts. If you do I squared R, obviously that's going to give you watts also, because that's where that equation came from. So in the chapter on resistance, I could give you a couple of problems that ask, you've got a current with a certain voltage and a certain resistance, how much power is consumed or dissipated by that circuit over time. And those are simple, straightforward plug-in problems. You either use power is IV or use power equals I squared R. There's not much more to say about those. So if you come across any power problems in the homework, those are the two equations you use. And again, really, really straightforward, simple stuff. The good thing about electrical circuit stuff and the stuff we're doing in class right now is it's a lot simpler and a lot more straightforward than the electric field stuff. So chapters 23, 24, 25, 26 are going to be a lot more straightforward than the Gauss's law stuff and the integrating to find electric field. So the really nasty part of the semester is over, and most of the stuff we're doing right now is just plugging numbers into equations. That being said, what we're going to cover next is Kirchhoff's rules for complicated multi-loop circuits, and those are pretty ugly, but that'll be the last sort of really complicated thing we do in this unit.